Okay, this is lesson 47, circles and inscribed angles. So just start off with a few definitions. Inscribed angle. It's an angle whose vertex is on a circle and whose sides contain chords of the circle. So if you look over here, angle ABC is the inscribed angle, ABC. The reason it's inscribed is because the vertex is on the actual circle itself. So when you see this happen, where there's an angle where the vertex touches the circle, that's what you call an inscribed angle. Okay, moving on to intercepted arc. It's the arc formed by an inscribed angle. So if we look at this same diagram, you'll see that this arc here was formed by this inscribed angle. So the arc, so it looks like a cone kind of. This cone part, the curved part, that's the intercepted arc of the inscribed angle. So the way you'd write that is arc ABC with this little symbol above it. Now moving on to some theorems. Theorem 47.1. It's the measure of an inscribed angle is equal to half the measure of its intercepted arc. So look over here at this equation. It's saying that the angle is half of the arc. Notice here x and then 2x. So if this angle were 5, the arc would be 10, and vice versa. If the arc were 18, then the angle would be 9. Okay. The next theorem, 47.2, says that if an inscribed angle intercepts a semicircle, then it is a right angle, which makes sense, right? Look at this diagram here. Notice how this inscribed angle makes a semicircle, right? Which means if this is 180, and half has to be 90, okay? So if an inscribed angle makes a semicircle, then you know automatically that's 90 degrees. Next theorem, 47.3, if two inscribed angles intercept the same arc, then they are congruent. This also makes sense. Look at this diagram over here. I want you to only picture this inscribed angle here. Do you see its arc, AB, right? Well, now I want you to picture only this inscribed angle here. It also has the same arc of AB. So when that happens, you know that angle 1 is congruent to angle 2 because they have the exact same arc. All right, and it'll always look like this bow shape. So when you see the bow shape, know that these two angles are congruent. Okay, next theorem, 47.4, if a quadrilateral, remember, four-sided shape, is inscribed in a circle, it has supplementary, what does that mean? Supplementary means 180, opposite angles. So look right here. You see how M and O are opposite angles? Well, they are 180. You see how P and N are opposite angles? Well, they're also 180. And that only happens when a four-sided shape is inscribed inside of a circle. So that's important to remember as well. Okay, let's work some problems together. Looking at this diagram right here, they ask us to name the inscribed angle in circle M. So take a look at this real quick and see if you can name the inscribed angle in that circle. It's angle JKL, because remember, the vertex has to be on the circle in order for it to be an inscribed angle. The next question says to name the arc intercepted by that angle. So look right here. The answer is JL, and we have to use the little symbol up above it as arc JL. Now, they're telling me in this third question that if the angle JML is 52, see right here, this central angle is 52, then what is the inscribed angle measure? Well, if this is 52, this is 52. Remember how arcs are congruent to their central angles? So if you know one, you know the other. So then that means that this is 52 degrees as well, which means that is half of 52. So 52, half of that is 26 degrees. That is the angle JKL. All right. Moving on over here, where it says find the measures of both the angle FGH and of arc GJ. So they want us to find both of those. So we're going to look right here at the 36. We need half of that to find angle FGH. So 36 divided by 2 is 18 degrees. So that's the angle FGH. We're not finished because we have to find arc GJ. Well, we know that this angle is 48, which means we double it to find the arc, right? So 48 times 2 is 96 degrees. So that is arc J. All right, down here it says find the measure of angle XYZ. So where is that? XYZ. So they want us to find this one right here. Well, if you think back on the theorem that I told you looks like a bow tie, that means that this one shares arc XZ as this one shares XZ, which tells me these two are congruent. So we can set that up as 2C plus 9 equal to 3C. And then we can move 2C over to find that C is 9, but we don't want to box that because they asked for the angle of XYZ. So we're going to plug the 9 that we found into the expression to get 18 plus 9, which is 27 degrees. That is angle XYZ. I guess we could have also, since they're congruent, we could have plugged the 9 in there. 3 times 9 is 27. Okay, notice this is a quadrilateral, and it tells us that opposite angles are what? Supplementary. So we need to set 4Z plus 3Z plus 5 equal to 180, because that's what supplementary means. We're going to combine like terms to get 7Z plus 5 equals 180. Then we're going to move the 5 over by subtracting it, so that leaves us with 175. Therefore, Z equals 25. We're going to be careful not to box that. We need to plug it back in. Actually, no, it says for U, right? Find angle U. So that would be this one right here. All right, so we are going to take 3, plug in the 25 plus 5, and we get angle U to be 80 degrees. All right, there's one more question over here to the left. It says to find the measure of angle 1, 2, and 3. So this is like a logic puzzle. You need to take a look at it and apply all the theorems that we've talked about to see how you can solve for all 3 angles. Now, the easiest one is right here. This is 76 degrees. So how would I find angle 3? You would divide the 76 by 2. You would half it to find angle 3. So half of 76 divided by 2 is 38 degrees. So we have angle 3. This is probably the next easiest to find because of the theorem that talks about the semicircle, right? Meaning if this is 180, that means this has got to be 90. That's a 90. So angle 2 is 90 degrees. Well, that's simple. We can find angle 1 now, right? Because if we take 180 and subtract the sum of the 90 plus the 38, we will get that angle 1, which is 52 degrees. And we have solved for all 3 angles. All right, last lesson, lesson 49. Introduction to solids. We're skipping lesson 48. The definitions that we're going to go over. solids. You already know what these are. We're just putting some definitions to it. You've been working with solids for a very long time. But basically it's a 3D shape, flat or curved surfaces. A polyhedron is any closed 3D figure formed by 4 or more polygons that intersect only at their edges. A cone, a 3D figure with a circular base and a curved lateral surface that comes to a point. A cylinder, however, has 2 parallel circular, right? Whereas a cone only has 1. Base and a curved lateral surface that connects those bases. And then a sphere is the set of points in space that are a fixed distance from a given point. So these down here are all solids. They're all 3D figures. A polyhedron is commonly known as a prism. And then, of course, you've got your cone, your cylinder, and your sphere. All right, more specifically, a pyramid is a polyhedron formed by a polygonal base and a triangular lateral face that meet at a common vertex. So you'll notice pyramids all have that point. I want to point out their bases. So see how this is a rectangular pyramid, a triangular pyramid, and a hexagonal pyramid. Now, this is always the base, this is always the vertex, this is always the edge, and this is always the lateral face. Moving on to prisms. It's a polyhedron formed by 2 parallel congruent polygonal bases connected by lateral faces that are parallelograms. So 2 parallel faces. Let me point that out for you in these diagrams here at the bottom. You see how there's 2 parallel triangles. That's why this is a triangular prism. There's 2 parallel hexagons, which is why this is called a hexagonal prism. 2 parallel rectangles, rectangular prism. Okay, once again, you got your bases, you got your lateral face, you have these edges, which are the lines, the points, vertex, and the faces are the shapes. All right, you're going to want to make sure this is in your formulas chart. It's called the Euler's formula right here. It helps you find vertices, edges, and faces using this formula. So take a second to solve for this one. It says how many faces, so you're solving for F, does a polyhedron with 12 vertices, so that tells you what your V is, and 18 edges, so that tells you what your E is. So plug those values into this formula and solve for the number of faces. Okay, vertices is 12 minus edges is 18 plus F, that's what we're solving for, so we don't know how many faces it has, equals 2. We combine like terms over on the left and we get -6 plus F equals 2. We add the 6 to the other side, which means the number of faces is 8. All right, last question on this page. Classify, that means name this polyhedron. Take a look, find the parallel faces, count their sides, and see if you can name this figure. Now, you'll notice 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's called a pentagon. It has 2 parallel faces, so we're not going to call it a pyramid because it doesn't come to a point. We're going to call this a pentagonal prism. Pentagonal prism. All right, that's it for this batch.